Gotcha. Can you guys see the screen now?
Yeah. All right.
Yes.
Good morning, everyone. We are Team Volter Fraud, and today we're going to present on the profitability of projects in an increasingly renewable grid. In the past 10 years, we've seen rapid solar deployment driven mainly by 80% drop in PV system prices. And this trend leads to vastly different dynamics in the wholesale energy market. Specifically, we believe that this will lead to the fattening of the duck curve, meaning lower prices in the midday and higher prices in the evening. This assumption will heavily impact on the profitability of solar projects going forward, as we will now show you in this presentation.
Thanks for that, Kathy. So I'm going to dive a little bit into the short-term solutions involving financial and physical hedges, which can make investing in renewable energy more attractive to investors. So we wanted to assess this as a case study. So for our case study, we chose the California market as it's a market which is becoming saturated with renewable energy. So we chose a 30 megawatt solar project. And to make things very as accurate as we could, we accessed the energy price data with time at an hourly increments from the California ISO database. We took this at an hourly basis for an entire year and projected it throughout the years until the year 2040. We then took historical hourly output from a California solar farm, scaled it to the 30 megawatt size that we decided on, and by multiplying the power produced by this solar farm by the price, the instantaneous price, we're able to project yearly revenues as the market becomes saturated with renewable energy. So let's go over the findings from the study. So first, we found that if the solar farm is operating in a pure market, merchant market, the cumulative NPV over time from the year 2020 to 2040 actually never crosses zero. This means that we are unable to recover the capital expenditures we initially put in. So this means that without further innovation in this market, solar energy will not be a valid investment. So the first venue we looked into is a traditional PPA. And as you can see, it makes substantial improvements. We're able to improve our revenue by over 84% compared to the pure merchant case. However, we're still unable to recover our CapEx, meaning that without any more innovation, traditional PPAs, as the renewable energy market saturates, will not be sufficient. So to cover this gap, we began thinking about what if we used energy storage using lithium-ion batteries. And as you can see in the upper right, this is what the curve would look like. We would store energy when we are producing our peak power, and then we would release that energy onto the grid when it is most expensive. And we do find that this is able to improve our revenue. And by optimizing these solar and storage combinations, we're able to improve our revenue by 114% over the base case of operating without energy storage. However, as you can see in this graph, the CapEx is very large at the beginning because we have to invest in additional money into this energy storage. So in its current state, with the current prices of lithium-ion batteries, the implementing of energy storage is not sufficient to make PV profitable. We project that we would need a 50% decrease in the capital expenditures for profitability to follow. So what does that mean for Macquarie, and what does that mean for the future of hedging practices? In our eyes, we must rely on PPAs today to increase profitability, but within the next 5 years, we believe battery innovations will be sufficient to decrease CapEx expenditures by over 50%, in which case solar fields could operate as merchants in a wholesale market and turn a profit. And we believe investment should be held off until this decrease in CapEx can occur.
So for long-term solutions, we actually want to solve the fundamental problem. So inverting the duck with supply-driven demand. So what's the actual problem we're having? Is that we're having a very flexible supply, but we have very rigid demand. So how can we actually make a flexible demand that can offset this additional supply of renewables, which is very flexible? So we're thinking, what if we can have technologies and industries which we can turn on or activate once we have this oversupply? But then, which industries would actually use intermittent power? So we're thinking heavy electricity users like hydrogen production and CCS, currently restrained with electricity prices, factory equipment we don't need 24/7, and technology that don't need a constant supply of power, like charging the electric fleet. But then how do we actually make intermittent power attractive? So what we want to do is we want to let the user set the prices. So for regular consumers, you would have an app and a smart power outlet. You would say, okay, my laundry machine, turn it on once the power hits this price. For enterprise, for small equipment, same thing, smart power outlets. For production plants, for large production plants like the hydrogen, we could have contracts. You could say, okay, turn on my hydrogen plant once, once the power hits a certain value. Next slide, Simon. So we hope, thank you for attention, and we hope that with your help, in no time, we'll have widespread Volter fraud. And we're thinking Volter fraud in Arizona, Volter fraud in Pennsylvania, Volter fraud even in Georgia, Voter fraud everywhere. Thank you.
Cool. Thank you. One question I had, if you go back to your slide 8, you have your base case with no storage, and then you have all the different storage sizing that you had kind of gone across. If I'm interpreting that graph right, it actually looks like the NPV for all of these storage cases ends up coming in lower than just the base PV case, which would suggest you may not want a battery. I wonder if you could just speak to that and explain that.
Yeah, so that's a great point. So as you can see, the base case starts out with a CapEx of around $40 million, whereas the storage scenarios have CapExes between 60 and $85 million, depending on how much storage you invest in. However, what I want to draw your attention to is on the right of this curve. You can see that in the base case, the curve flattens out significantly, whereas in the storage cases, you can we are still gaining ground. And essentially, what this means is when we have storage, we're able to turn greater yearly revenue. And so, while we're unable to recover in about 20 years, if, for example, you were able to cut the capital expenditures of the battery storage in half, you would be able to shift all of these curves upward substantially, and you would see that with the reduced cost of batteries, we would actually be able to have higher NPV with solar and storage as opposed to the base case. Just to put some numbers to it, in our simulation, the yearly revenue in the base case was around $2 million, and the yearly revenue in 2040 for the energy storage situation was around $4 million.
Okay, so the increase in revenue is growing over time, is what you're saying, even though it's more negative.
That's right.
We were assuming kind of battery prices would be stagnant. So if those drop, then you'll start seeing NPV, increase considerably for storage.
Got you. Did you look at all around the impact of renewable energy credits, REC credits, particularly for solar, and kind of the impact that those credits are going to have on California? So, California does have a 100% renewable mandate. It has to hit 100% by 2045. Solar does get paid from kind of the wholesale market price, but also the renewable credits. I was just wondering if you had looked at that piece at all.
Yeah, so I can speak to that. So the reason why we are somewhat comfortable with these negative NPV values is that this analysis really focuses on the profitability within the wholesale energy market alone, but taking into account these various other revenue streams, I think this would potentially make the project positive. So as you said, there are also REC revenues as well as capacity values that are in addition to wholesale energy market values. And so one reason why we did not decide to consider those is because in the coming years, as more renewables are going to come into play, these values of RECs and I think will be decreasing because we'll just be oversaturated with renewable energy.
And with or without the inclusion of RECs, the general trends are still the same, right? We see that PPAs are very helpful, and solar and storage can be helpful as well once we reach a certain threshold when the CapEx of those storage systems becomes lower.
Got it. And then one important assumption in this is you kind of took the 1-year benchmark for pricing. And so essentially you would assume that kind of that distribution, like the spread of kind of low prices during midday, high prices during evening, stays relatively kind of the same over the forecasted period. So you are kind of assuming that kind of differential stays. So another thing that could impact this is if that starts really changing in a material way. Is that right? Am I understanding that right?
Yeah, you're absolutely right there. So how the market changes would change the shape of the graph of the energy curve and everything, and you'd hope to reduce the volatility. But we had to make some assumptions in this short time period to be able to make some valid analysis. Yeah. Right? So our essential strategy was we assumed that over the course of the next 20 years, the cost of energy would remain constant. However, the additional saturation due to renewable energy would exacerbate, make the valleys deeper and the peaks higher. And that's what you can see what we've done here. Essentially, over the average price remains the same between the orange 2040 projection and the current 2020 prices, but we exacerbate the peaks and the valleys.
Thank you, Volta Fraud team. Time's up. We're moving on to the next team. Thank you.
Thank you so much.
Thank you.
Great.
Have a good one.
Thanks, guys. Thank you.